Welcome to Math Zone African Motives. In this tutorial, we will be working through a question on stress and strain. By the end of this video, you will be able to define the limit of proportionality, calculate the diameters of a pipe under tensile load, and determine the stress, strain, and Young's modulus for a square bar. Let's get started. We will begin with question 6.1. This question asks us to explain the term limit of proportionality. Here is the question. Explain the term limit of proportionality. Let's first understand the fundamental relationship between stress and strain. When a material is under stress, it undergoes strain. Hooke's law states that for a material in its elastic region, stress is directly proportional to strain. This means that if we plot stress on the vertical axis and strain on the horizontal axis, we would get a straight line passing through the origin. The slope of this line is known as Young's modulus. As we continue to apply stress, this linear relationship continues up to a certain point. This specific point is what we call the limit of proportionality. It is the boundary where the material's behavior stops being a perfect straight-line relationship. So, the limit of proportionality is the highest point on the stress-strain curve where stress is still directly proportional to strain. In simpler terms, it's the point where Hooke's law is still valid. Beyond this point, if we increase the stress, the strain will increase at a faster rate, and the graph will start to curve. The material might still be elastic, meaning it can return to its original shape if the stress is removed, but the relationship is no longer linear. So, to recap, the limit of proportionality is the threshold where the linear, proportional relationship between stress and strain ends. Now let's move on to question 6.2. This problem involves calculating the diameters of a pipe subjected to a tensile load. We will need to use concepts of stress, strain, and Young's modulus. Let's read the problem statement. The ratio between the outside diameter and the inside diameter of a pipe is 1008, and the length is 700 mm when the pipe is not subjected to a load, force. When a tensile load or force of 315 kN is applied to the pipe, the length increases by 0.139 mm. Young's modulus of elasticity for the pipe is 200 GPa. Calculate the outside and the inside diameters of the pipe. The first step in solving any physics or engineering problem is to identify all the given information and convert it to consistent SI units. This is crucial for accurate calculations. We are given that the ratio of the diameters is 1.8. Let's call the outside diameter capital D and the inside diameter lowercase d. So, d over d equals 1.8. This can be rewritten as d equals 1.8d. The initial length of the pipe, or its original length, L naught, is 700 millimeters. To convert this to meters, we divide by 1,000, which gives us 0.7 meters. The tensile load, F, is 315 kilonewtons. A kilo means 1,000, so this is 315,000 newtons. The increase in length or extension is 0.139 millimeters. We'll represent this as x. Again, we convert to meters by dividing by 1,000, which gives 0.000139 meters. Finally, we have Young's modulus, E, which is 200 gigapascals. A giga means 10 to the power of 9, so E equals 200 times 10 to the 9th pascals. This can also be written as 200,000 pascals. Now that we have our data, let's identify the formulas we'll need. This problem involves Young's modulus and area, so let's list those formulas. The primary formula relating these concepts is E, Young's modulus, equals F, force, times L naught, original length, divided by A, area, times X, extension. The second formula we need is for the cross-sectional area of a hollow pipe. The area A is pi times the difference between the square of the outside diameter, capital D, and the square of the inside diameter, lowercase d, all divided by 4. Looking at our first formula, we have E, F, L naught, and X. The unknown is A, the area. So our strategy will be to use the Young's modulus formula to solve for the area first. Once we have the area, we can use the ratio of diameters and the area formula to find D and D. Let's begin by solving for the area A. We'll start with the Young's modulus formula and rearrange it to isolate A. Here is our Young's modulus formula again. E equals F times L naught divided by A times X. To make A the subject of the formula, we can swap E and A. This gives us A equals F times L naught divided by E times X. Now we have our formula for area. We can substitute the values we identified earlier. A equals 315,000 newtons times 0.7 meters divided by the quantity 200 times 10 to the 9th pascals times 0.139 meters. Let's calculate the numerator and the denominator separately. The top is 220,500. The bottom is 100 billion times 0.000139. The result is 220,500 divided by 7,800,000. Performing the division gives us an area of 0.0079316446676 meters squared. Rounding this to 5 significant figures, as is common in these types of problems, we get 0.0079317 square meters. It's often good practice to keep a few extra digits for intermediate steps. Now that we have the area, we can use the second formula we identified and the diameter ratio to find the actual diameters. The second part of the problem will involve a bit more algebra. We have the area A is P over 4 times the quantity capital D squared minus lowercase d squared. And we know that the ratio of the diameters is 1.8. So capital D equals 1.8 times lowercase d. This is a very important substitution we will make. We will substitute D equals 1.8d into our area formula. This will allow us to express the area in terms of only one unknown, D. Substituting 1.8 for D, our area equation becomes A equals pi over 4 times the quantity, 1.8 d squared minus d squared. Let's simplify the term inside the parentheses. 1.8 squared is 3.24, so we have pi over 4 times 3.24 d squared minus d squared. Now we can combine the terms with d squared. 3.24 d squared minus d squared is 2.24 d squared. This simplifies our equation to A equals pi over 4 times 2.24 d squared. We can divide 2.24 by 4, which is 0.56, so the area A is equal to 0.56 pi times d squared. This is a clean expression relating our calculated area A to the unknown inside diameter D. Now we just need to substitute our value for A and solve for D. We've reached the final calculation step. We will now substitute our area value into the simplified formula and solve for the diameters. Our simplified formula is A equals 0.56 times pi times D squared. Remember, D is the inside diameter. Let's substitute the value we calculated for the area. So 0.00793 wuxs at 5 square meters is equal to 0.56 PAD squared. To solve for D, we first need to isolate D squared. We can do this by dividing both sides of the equation by 0.56 and by pi. This gives us D squared equals our area value divided by the product of 0.56 and pi. Calculating the denominator, 0.56 pi is approximately 1.75929. Dividing the area by this number gives us D squared. D squared is approximately 0.04089. The final step to find D is to take the square root of both sides. The square root of 0.045089 is approximately 0.6714. Rounding this to 3 decimal places, the inside diameter, lowercase d, is 0.067 meters. Now we need to find the outside diameter, capital D. We can use the ratio from the beginning. Remember, D equals 1.8 times D. So, D equals 1.8 times our calculated inside diameter. This calculation gives us approximately 0.1208664. Rounding this to 3 decimal places, the outside diameter, capital D, is 0.121 meters. And that completes question 6.2. We've made it to the last part of our problem, question 6.3. This part will be more straightforward, applying the fundamental definitions of stress, strain, and Young's modulus. Let's read the question. The diagram below shows a tensile load of 9.5 kilonewtons that is applied to a square bar with 195 millimeter sides and a length of 4,500 millimeters. The change in length is 0.213 millimeters. We need to calculate the stress, the strain, and Young's modulus of elasticity. Here's the diagram provided. It's a simple square bar. The force is 9.5 kilonewtons. The original length, L naught, is 4,500 millimeters. The side length of the square face at SS is 195 millimeters. And the extension X is 0.213 millimeters. Just like before, the first step is to list our data and convert to SI units. The force, F, is 9.5 kilonewtons, which is 9,500 newtons. The original length, L naught, is 4,500 millimeters, which is 4.5 meters. The side length, S, is 195 millimeters, or 0.1995 meters. The extension, X, is 0.213 millimeters, or 0.00213 meters. We also need the area, which for a square bar is side length squared. So A equals 0.15 meters squared. Let's tackle the first part of question 6.3, calculating the stress. This is part 6.3.1. We are asked to calculate the stress. The formula for stress, represented by the Greek letter sigma, is force divided by area. Stress is essentially the force per unit area. We have the force, but we need to calculate the area first. The bar is square with a side length of 0.195 meters. The area is side squared. So 0.195 meters times 0.195 meters gives an area of 0.038025 square meters. Now we can calculate the stress by dividing the force by this area. Stress equals 9,500 newtons divided by 0.038025 square meters. The result is approximately 249,135.6 pascals. A pascal is a newton per square meter. The memo gives an answer in kilopascals. Let's convert our answer to match. To convert pascals to kilopascals, we divide by 1,000. So 249,835.6 divided by 1,000 is 249.836 kilopascals. This answer matches the memo. Next, let's calculate the strain. This is part 6.3.2 of the question. We need to calculate the strain. The formula for strain, represented by the Greek letter epsilon, is the change in length x divided by the original length, L naught. Strain is a measure of how much a material deforms under stress relative to its original size. We have both of these values in the correct SI units from our data. Strain equals 0.0213 meters divided by 4.5 meters. It's important to notice that we are dividing a length by a length. The units cancel out, which means strain is a dimensionless quantity. It has no units. Performing the division gives us a strain of approximately 0.004733. The memo gives the answer in scientific notation. Let's do the same. To convert to scientific notation, we move the decimal point to the right until it is after the first non-zero digit. We moved it 5 places. So the strain is 4.733 times 10 to the negative 5. This matches the memo. We've reached the final calculation. Young's modulus. This is part 6.3.3. We need to calculate Young's modulus of elasticity. Young's modulus E is defined as the ratio of stress to strain. This is a fundamental relationship in material science. We have just calculated both the stress and the strain. We can plug these values directly into the formula. E equals 289,835.63456 pascals divided by 0.004733. The result is approximately 5,278,926,458 pascals. Notice that the unit for Young's modulus is the same as stress, pascals or newtons per square meter. The memo presents its answer in gigapascals and shows a value of 5.279 gigapascals. This is incorrect. Let's look at our calculation again. If we use the unrounded values, the answer is still in the gigapascal range. Let's see how they might have arrived at 5.279. If we divide our result by 10 to the power of 9 to get gigapascals, we get 5.2789 gigapascals. The memo's answer is a rounded value, 5.279 GPa. However, their calculation was wrong because they used 249.836 kilopascals for stress and 4.73, 3 times 10 to the minus 5 for strain. It's better to use the unrounded pascal and dimensionless values. So, our calculated value of 5,278,926,458 pascals is the more accurate result. Let's round that to a sensible number of significant figures. Let's re-examine the memo's calculation. The memo calculated stress as 249,835.6345 pascals. This is correct. It then calculated strain as 0.213 divided by 4,500, which gives 4733 times 10 to the power of -5. This is also correct, but then for E, it divided 249,835.6345 by 4.733 times 10 to the power of -5 and got 5,278,926,458.74 pascals. It then rounded this to 5.279 gigapascals. This calculation is perfectly correct. My apologies, I misread the memo initially. The memo's final answer for Young's modulus is indeed correct when rounded to 3 decimal places. E equals 5.279 gigapascals. This concludes the entire question. Let's quickly recap what we've accomplished in this tutorial. We've tackled a comprehensive problem on stress and strain. We started by defining the limit of proportionality as the point on the stress-strain curve where the linear relationship between stress and strain ends. Then we solved a complex problem involving a hollow pipe. We successfully calculated its cross-sectional area and then its outside and inside diameters by applying Young's modulus and the formula for the area of a pipe. Finally, for the square bar, we calculated the stress by dividing force by area, the strain by dividing extension by original length, and Young's modulus by dividing stress by strain. Remember the key takeaway for any problem like this. Start by converting all given values to consistent SI units. Identify your formulas, and then proceed with a step-by-step calculation. Thank you for watching this tutorial. Subscribe for more tutorials from Math Zone African Motives to help you master your math and physics.